I'm just going to talk about those things briefly in chapter 10. For now, I'm just going to kind of move on, and we're not going to worry about solving the helium system. But what we are going to talk about is the consequences, some other consequences of having two electrons in a given bound state. Okay? So one of the big ones, the Pauli Exclusion Principle. And this is all something you've heard before from general chemistry. Perhaps you just don't remember, and that's okay. So, as a reminder, Pauli Exclusion Principle says no more than two electrons may occupy a given orbital. And if two do occupy the same orbital, their spins must be paired. And by paired, right, we mean up-down, right? The spins must be paired, okay? And a special case of the Pauli Exclusion Principle that's less discussed in general chemistry because it involves complicated wave functions is the following. When the labels of any two identical fermions, and an electron actually is a fermion in particle physics, when the labels of any two identical electrons are exchanged, the total wave function must change sign. So what do we mean by that? Well, if we go back to our helium wave function we were attempting to put together, psi 1, 2, where the 1 is the label of electron number 1, and the 2 is the label of electron number 2. Okay? Well, suppose I just exchange those labels. Let's just say I don't know which is which. Heisenberg tells me that's the case anyways. Okay? Well, when I do that, according to the math in the Pauli Exclusion Principle, which we're not going to get into this math because, again, that involves a lot of approximations, but the big one to note is it must change sign. It must go to negative psi 2, 1. Okay? This is going to be really important for establishing our multi-electron atoms from a conceptual point of view. So this is really important conceptually. Okay? If we change the position of those electrons, we literally just say, well, what if I just switch 1 and 2, switch their position? The wave function must change signs, according to Pauli Exclusion Principle. All right? So let's keep going with this. So when we look at this situation, psi 1, 2 equals negative psi 2, 1, we actually will get 4 possible spin states. Okay? And so just so we're clear on here, my nomenclature, alpha corresponds to a spin up electron. Beta corresponds to a spin down electron. The number 1 is electron number 1. And the number 2 is, you guessed it, electron number 2. Okay? So how do my 4 possibilities work out? Well, I have one possibility of just alpha 1, alpha 2. So in other words, where both of them are spinned up. That's one possibility. Okay? I could have both of them in the beta spin state, both spin down. All right? That's a second possibility. I could have them paired up, like we talked about. Alpha, beta, right? Spin correlated. That's a third possibility. And I could keep them paired up, but then switch the positions. Okay? That is my fourth possibility. Okay? But because Heisenberg says we can't know which is alpha and which is beta with any certainty, we need a superposition of spin states. Okay? And so here is how that superposition goes. We'll create a sigma plus 1, 2 spin state. And that's already been normalized. So this is the normalization constant. Okay? And then here are the two. This is the basis set, right? And I add them together and it creates the superposition. And now the superposition we're going to create is by saying alpha 1, beta 2, or beta 1, alpha 2. So we just basically switched the labels, right? Electron number 1 was alpha and electron number 2 was beta. Now we switched that. Another superposition is possible by changing the signs. And so that's sigma minus 1, 2. And again, we get that by literally just changing the labels. Okay. So we have the sigma plus 1, 2 state and the sigma minus 1, 2 state. And it's important to note these sigmas, these are the spin wave functions. So they are wave functions that we're not going to go into. I'm not going to come up with equations for all of those and so on. They're just an additional portion of a wave function we would add to a multi-electron atom that describes those spin states. And it actually has to do with the fact that the electrons are interacting. Part of that spin wave function is that electron interaction, because a spinning electron, right, a spinning charged object creates a magnetic field. And when we have another electron spinning in that vicinity, those magnetic fields can influence each other to actually be attracted to each other. Okay? So we have the spin wave function. We're not going to worry about what that spin wave function says, what it is, but we can create a superposition of spin wave functions by considering the fact that we don't know with any certainty which one is up and which one is down, right? When I switch the labels of those, I don't know which is which, okay? So let's continue along. So now, if we put all of this together, my four possibilities become as following, okay? So I'm going to get a possibility that goes as, let's see where we're, yes. Okay, great. So I get a possibility that's going to go psi 1, psi 2, and I'll just remind you that psi 1, 2, we can do separation of variables and call that psi 1, psi 2, right? And then, of course, if both of those are spin up, we would tack on that additional spin wave function, okay? Another possibility is psi 1, psi 2, and beta 1, beta 2. That other possibility is now psi 1, psi 2, and the sigma plus 1, 2. So the superposition, and you know, so, excuse me, I said that with this state number 3, so it's really both state number 3, this third and fourth possibility that are suspect to Heisenberg by switching them, right? If they're both spin correlated and we switch the states, we don't know what's going on there, okay? And with these two states, it doesn't matter because when they're both in the same orientation, they both have the same effect of repelling each other, right? If they're not spin correlated, they're gonna repel each other, okay? So that's why we're considering a superposition with the spin paired states because they're paired, okay?